Late August 1944, 06:15 hours, observation post 4, northern France. A crumpled morning report sat on the desk while the technical officers of Flak Regiment 155W tried to make sense of the numbers in front of them. The interception figures defied every rule of ballistic probability taught in Luftwaffe technical schools across the Reich. 82% destroyed. That could not be right. Yet through their field glasses, the German spotters had seen something with their own eyes that contradicted everything their intelligence services claimed about Allied anti-aircraft power. The V-1 flying bombs fired toward London before dawn were being knocked down at rates no one could explain. Not by fighters pulling risky pursuit curves, not by barrage balloons snagging wings and tails. They were being torn out of the sky by anti-aircraft guns over the coastal belt, shells bursting with uncanny precision near the missiles, detonating close enough to kill without a direct hit. At Flak Regiment 155W headquarters, housed in a commandeered chateau, the commander of the V-1 campaign, Oberst Max Dautel, received the day's summaries with mounting alarm. Over the course of the summer, the share of flying bombs destroyed by the coastal gun belt had climbed from 17% in June to 74% by late August, peaking at 82% on one remarkable day in that final week. It was the opening act of the deepest technological shock the Wehrmacht's weapons experts would face in the war. Neither Dautel nor any German scientist understood that they were watching one of the Allies' most tightly guarded secrets go to work. The device, kept under security as strict as the atomic bomb program, was the proximity fuse codenamed the VT for variable time diffuse. It was methodically shredding Hitler's terror weapon with accuracy German physics said could not exist. The chain of events started 10 weeks earlier, on June 13, 1944, exactly 1 week after D-Day. Stung by the Allied landings in Normandy, Hitler unleashed his long-promised Vergeltungswaffe, vengeance weapon, against London. At 4:25 a.m. that morning, the first V-1 struck the city, hitting Grove Road in Bow, wrecking a railway bridge and nearby houses. 6 people died, 30 were injured, and 200 lost their homes. The weapon was the fruit of years of German research, a pilotless aircraft driven by an Argus AS-109 pulse jet, carrying roughly 850 kilograms of amytal and cruising at about 640 kilometers per hour. It was the world's first operational cruise missile, and the German High Command believed it could break Britain's will. Major Walter Dornberger, who oversaw the V-weapons effort at Peenemünde, calculated that even with a cautious 25% success rate, the V-1 could deliver more explosive force to London than the entire Blitz of 1940-41. Each missile cost about 5,000 Reichsmarks, far cheaper than dispatching a manned bomber and with no aircrew at risk. The Peenemünde team had reasons to be confident. They had pioneered advanced rocketry, fielded operational jets, and now deployed an unmanned strike aircraft. Dr. Robert Lusser, who designed the V-1's control system, concluded Allied interception would be nearly impossible. The flying bomb's 640 kilometers H-speed and variable altitude, anywhere from 600 to 2,700 meters, made it a tough mark. British fighters needed to exceed 650 kilometer H to overtake it and then close to within roughly 200 meters to fire. Dangerous proximity to a warhead that could destroy pursuer and target together. As for ground fire, the math looked even worse. The odds of a conventional timed shell scoring a direct hit on such a small, fast target were estimated at less than 1 in 10,000 rounds. That was not propaganda. It was standard gunnery science. Time-set fuses demanded precise prediction, exact calculations, manual fuse setting, and perfect timing. With the V1 speed, gun crews often had 30 seconds from detection to engagement. Oberst Max Wachtel, another veteran of anti-aircraft warfare, understood these limits from both sides. During the campaign, the Germans would launch 9,521 VA-1s from fixed sites at Britain, with thousands more fired at other targets, bringing total wartime launches to roughly 25,000. Within days of the first strikes, worrisome signals reached German intelligence. British defenses were adapting with suspicious speed. By late June, interception rates rose from around 10% to about 24%, higher than expected, but still plausible. Then July arrived, and the numbers stopped making sense. German technical officers tracking effectiveness noticed British batteries, claiming V1 kills while expending far fewer shells than models predicted. Observers along the French coast saw V1s flying steadily toward England, suddenly encircled by flak puffs and then pitching out of the sky, even though the bursts looked too far away for direct hits. Unseen by German analysts, the Allies were using proximity fuses that turned near misses into certain kills. The technology had already proven itself in the Pacific. In January 1943, USS Helena brought down a Japanese dive bomber with shells that detonated when their electronics sensed closeness to the aircraft. German intelligence missed the trend. The Oslo report of November 1939 had mentioned Allied work on proximity fuses, but German scientists dismissed the warning as deception. They had tried to build something similar. More than 30 concepts were explored, but none reached the field. The consensus in German engineering circles was that proximity fuses were impossible. The barriers looked overwhelming, shrinking radio transmitters and receivers to fit a shell, building vacuum tubes that could survive 20,000 G, creating batteries that would wake up after years on a shelf, and making the whole thing at scale. Yet by August 1944, American factories were turning out about 40,000 VT fuses a day. In the last week of August 1944, the proximity fuse reached peak effect. The British had reorganized their air defense architecture. Gun positions were resighted from the North Downs to the South Coast to form a dense gun belt, and American SCR-584 radars provided automatic target tracking. Most critically, the batteries used VI-fused ammunition tailored for the V1 threat. The coastal alignment also meant dud shells fell into the sea, denying the Germans any chance to recover intact examples. As each V1 crossed the shoreline, it entered a kill zone where technology overruled probability. The SCR-584 locked onto targets, computed trajectories, and fed firing data directly to the guns. Inside each fuse, miniature radio circuits built with rugged tubes from companies like Sylvania and Western Electric listened for reflections. When the signal pattern showed the shell was close enough, Thyratron switches fired the detonator, blasting the V1's thin skin with a cloud of steel. On the best day that week, coastal guns destroyed 82% of incoming V1s, an outcome German engineers had labeled physically impossible. The 82% figure set off crisis discussions at headquarters. BTAL suspected sabotage. Emergency audits found nothing wrong with the missiles. Test shots over German ranges looked normal. The nightmare existed only where British guns defended their coast. German specialists concluded the British had fielded a revolutionary anti-aircraft system, but they could not identify its core without a captured specimen. They tried adjustments, different altitudes, larger salvos, more night launches, exploiting weather, but nothing worked. The kill rate stayed ruinous. At Peenemünde, researchers faced an uncomfortable thought. If the Allies had proximity fuses, they had conquered a problem Germany had declared unsolvable. Efforts to crack the secret intensified and failed. Security around the fuse was almost perfect. Production was split among more than 100 factories. Workers knew only their own narrow tasks. Even the term variable time was chosen to mislead, implying a fancy time fuse rather than a sensor. By 1944, a massive chunk of America's electronics capacity was dedicated to VT production. By war's end, 22 million proximity fuses would be built at a cost exceeding $1 billion 1940s dollars. The Crossley Corporation alone made more than 5 million, nearly a quarter of the total. The numbers laid bare the industrial mismatch. While Germany assembled V1s with coerced labor, America transformed civilian radio and appliance firms into fuse makers. Daily output peaked near 40,000 units. Unit costs plunged from about $732 in 1942 to roughly $8 by 1945. Crossley, once a radio and refrigerator brand, fielded a 10,000-person workforce, turning out about 16,000 fuses a day at the top. Sylvania devoted its entire vacuum tube research arm to ruggedized miniatures, producing around 400,000 tiny tubes daily, supplying roughly 95% of what the program needed. Germany handcrafted brilliance in small lots. America mass-produced innovation at scale. The engineering itself was extraordinary. A VT fuse had to survive gun launch 20,000 times the force of gravity, spin at about 25,000 revolutions per minute, and endure heat and cold. Sylvania adapted hearing aid tube designs and then reinforced them to live through the abuse. Long shelf-life batteries had to stay dormant for years and then activate instantly when the shell was fired. A tiny radio transmitted continuously. When reflection signaled a large object nearby, the circuit triggered detonation. The idea sounded simple, but it demanded solutions that German engineers had written off as fantasy. Quality control was relentless. Every fuse faced multiple tests. Random samples were proof-fired from real guns. Rejection rates stayed under 2%. Remarkable precision at massive volume. By September 1944, the V1 assault on Britain had been blunted. Of the 9,521 V1s fired from ground sites at the United Kingdom, only 2,515 reached London, killing 6,184 people and injuring 17,181. Tragic as those losses were, they were a fraction of what Germany had intended. General Frederick Pyle, who commanded Anti-Aircraft Command, estimated that without VT fuses, V1 casualties would have been 4 to 5 times higher. The fuse spared London from a far greater disaster. Germany shifted to more night launches and then leaned on the V2 rocket, which traveled too fast and too high to intercept. Those measures brought spectacle, not strategy. The V1 became an expensive failure that devoured resources needed for fighters and anti-tank guns. German intelligence never solved the puzzle. Not a single intact proximity fuse fell into their hands during the V1 campaign. Incredibly, during the Battle of the Bulge, German troops seized an American ammunition dump that contained VT-fused shells and still did not recognize what they had. Their conviction that such devices could not exist blinded them to the truth. After the surrender, Allied interrogators found complete ignorance about the fuse. Oberst Max Wachtel told his questioners They suspected better radar or quicker setting time fuses, but never imagined thinking shells. When German scientists were finally shown captured VT fuses, they balked. Tubes surviving launch, batteries still good after years, circuits functioning after a cannon shock. Many judged themselves 10 years behind. Dr. Merle Tuve, who led development at the Johns Hopkins Applied Physics Laboratory, later observed that the program succeeded because scientists, engineers, and factory workers collaborated systematically, something a dictatorship struggled to foster. The proximity fuse proved that the war's outcome hinged as much on laboratories and production lines as on front lines. While Germany chased exotic wonder weapons, America poured effort into multiplicative technologies that made existing guns far more lethal. A proximity fuse could make an anti-aircraft battery 5 to 10 times more effective. Secretary of the Navy James Forrestal put it plainly, the fuse helped blaze the trail to Japan. Without its protection, the U.S. fleet's westward push would have been slower and bloodier. There was a moral contrast as well. The V-1 program relied heavily on slave labor. Tens of thousands of concentration camp prisoners died in underground factories that built the missiles. In the United States, workers volunteered for long shifts at premium wages, unaware of exactly what they made, but convinced it mattered. At Sylvania's Ipswich facility, more than 5,000 women worked 12-hour days on specialized parts. Only after the war did many learn they had helped save London from a terror weapon. Secrecy came at a price. British gun crews did not know why their special rounds worked, only that strict accounting rules applied. Every VT-fused shell fired at a V-1 was logged. Any unexploded rounds were secured at once. Naval vessels patrolled the channel to prevent recovery of duds. The vow of secrecy was so strict that Allied ground forces were barred from using VT-fused artillery until December 1944. Thousands of soldiers died earlier in the year because the risk of compromise was judged too great. Even so, using the fuse against the flying bombs was necessary. Protecting London during the invasion months was essential to the Allied strategy. In the end, the V-1 effort drained German strength while delivering little strategic value. Launching roughly 25,000 missiles consumed millions of Reichsmarks and diverted attention from aircraft and anti-tank weapons desperately needed on collapsing fronts. The reliance on forced labor added a grim moral weight. The proximity fuse, made by free workers in vast numbers, was defeating a weapon built through human suffering, a contrast fully appreciated only after 1945. The larger lesson was unmistakable. The fuse marked a turning point, victory through engineering and production rather than through a single, perfect weapon. Before the VT fuse, knocking down a V-1 took on average about 2,500 heavy shells. With VT, that figure dropped to roughly 100. In 10 weeks, the coastal belt's interception rate rose from 17% to 82%. Courage and training mattered, but mass-produced advanced electronics mattered more, and Germany could neither match nor fully comprehend that scale. By war's end, America had mobilized its electronics industry, employed more than 80,000 people, invested over $1 billion, and manufactured some 22 million fuses. The War Department declassified the program in September 1945 and called the proximity fuse one of the most important weapons developed during the war, surpassed, in effect, only by the atomic bomb. For the German scientists who had stared at inexplicable failures all summer, the revelation brought understanding and humiliation. They had believed the V-1 sat at the pinnacle of weapons technology. Learning it had been beaten by cheap, mass-produced electronics costing under $20 each was devastating. They had not been outfought so much as outmanufactured. The fuze's legacy flowed into modern air defense, radar altimeters, and electronic warfare. For many former German weapons experts, it remained a permanent reminder of wartime blind spots. The moral was simple. In modern conflict, producing good technology in huge numbers matters more than crafting exquisite one-offs. Germany built brilliant individual weapons. America built effective weapons by the million. On that extraordinary day, in late August 1944, when VT fused shells destroyed 82% of the incoming V-1s, the character of warfare shifted. The launch crews had done everything they knew how to do, designed advanced systems, trained skilled teams, found tactical wrinkles. They were still defeated by compact radios and vacuum tubes stamped out by the ton. London was saved by thousands of small blasts near their targets, blasts made possible by a technology German science had declared impossible. It was industrial democracy, outproducing totalitarian engineering, mass production, eclipsing hand-worked perfection. Simple ideas multiplied, beating complex wonders. The Germans never discovered what, exactly, was hitting their V-1s as they fell burning from the sky. They only learned the truth long after it mattered. The proximity fuse had turned Hitler's vengeance weapon into London's shield. In the end, America's greatest triumph was not only on battlefields, but in factories where millions, many of them women who never knew the details, built the tiny electronic brains that saved a city and changed warfare forever. Wow! The 82% interception achieved in late August 1944 stands as proof that in modern war, industrial capacity can break any miracle weapon. The proximity fuse was more than a device. It was evidence that a free society's ability to mobilize science and industry can overcome tyranny's forced brilliance. And it left German leaders insisting they were winning a war their technology had already lost.